Hi, I'm Alistair, and in this video I'm going to show you how to create this electronic puzzle, which uses a load cell to measure the weight of one or more items hung from this hook. If the weight matches a value that is stored on the Arduino within a certain tolerance, this relay will get activated. That's going to supply power to this MagLock, which is going to unlock and release this catch here. So just to show you in action, I've got a number of different items which I can try weighing here. But before I do that, what I'll do is I'll just put the output of the Arduino on the screen there so you can see the results of what I'm reading from this load cell. So at the moment, with no weight, I'm at 0. If I hang this rusty old chain on the hook, you'll see that value go up, but that's not the right value to activate the puzzle. So I'm going to remove that again. And instead I'm going to place this block of wood. Let's see if this does it. No, still nothing. The wood and the chain may be together. No. Okay, how about, in that case, what about my coffee cup perhaps? No, still not the right weight. So the only thing I have left to try is this rather nice ornate bell. And when I hang that on there, you'll see that that was the correct puzzle, and at least rather than falling on my lap as a change, the MagLock was shot across and dinged off my coffee cup. So that's the puzzle in action. Let me describe a little bit more in detail the different components that I'm using here and how it works. First of all, I'll get rid of that bell there. So the main sensor component that's being used in this puzzle is something called a load cell, or a strain gauge sometimes, and they come in different varieties and types, and they're used in different things. This particular model I'm using here is very similar to you'd have set in a set of digital weighing scales, for example. And what happens is that when a strain is placed on one end of the cell, it's like a metal bar, and it has a thin series of wires coming across it. And when the bar is put under a strain at one end, what it does is it causes those wires to compress underneath, and the ones over the top get put under tension. And that actually alters the resistance in those wires. And that's how these work, is that but they are a very small change in resistance caused by compression or tension of the weight of an object being placed on the end of it. Now, that change in resistance is not large enough to be detected directly by an Arduino, however. It's quite a small change. So in between the load cell and the Arduino, I've got a little module here called an HX711, and that converts the quite small analog signal from the load cell into a much stronger digital signal, which can be read by the Arduino. So that's put into two of the data pins on the Arduino, and that can be read by a simple analog read here. So I've got a code that has got a particular weight, a target weight set in it, and that weight was set equal to the weight of this bell. The Arduino constantly polls the load cell reading via the HX711, and if the target value matches the one set in code, what it does is it sends a high signal to this relay here. This relay has got 12 volts going into it on the other side, so when this is turned on, this is going to allow 12 volts to flow on this side of the relay to the MagLock, and the MagLock at that point released and spat the catch out. Now, I've actually used a different style of MagLock in this video than I have in some of my other projects, and that's deliberately because this subject actually came up quite recently on one of the Facebook groups that I'm a member of. So the normal style of MagLock I've used is one of the long bar style types, and that's what's called a fail-safe MagLock. And what that means is that they need to be continuously supplied with power in order to stay locked. If the power supply is turned off for any reason, either because there's a loss of power or because it's been turned off by a relay through an Arduino, something like that, the magnet de-energizes and the MagLock opens up automatically. Now, this is a different sort of MagLock, however. This is what's called a fail-secure MagLock. So with a fail secure MagLock, it's locked by default. So even with no power going to it, as there isn't at the moment, if I reattach that latch in there, that is secure behind the little mechanism here, behind the catch, and will stay locked even if the power is dropped, if I cut through these cables, if the power goes off, whatever. So it's kind of like the opposite. It needs to have current supplied to it, and when it does have current supplied to it, what it will do is it will kind of eject that latch, as you saw earlier. So these are good in the sense that they use much less, they have much less demanding power requirements while the puzzle is going on, because the whole time I was doing all this weighing up here, no power was being supplied to this at all. It's only at the point that the puzzle is solved, I send a brief pulse of current, just for 1 second. I activated this for, and then I can turn it off again. One thing I need to make clear though, you mustn't ever use this sort of MagLock to secure a door or something that someone could get shut in, any kind of space that a person can get shut in. You mustn't use one of these MagLocks, because if the power gets cut in your building or whatever, this will stay locked forever. So you must use a fail-safe one if you're securing some sort of area that a person gets stuck in. But if all you're doing is securing, let's say, a small box or a drawer in a desk or something like that, then this kind of MagLock is pretty good to use instead. So let me talk you through the wiring of the components that I've used in this puzzle. Starting with the load cell, because that's the most significant component that I'm using here. Now, my load cell didn't come with any instructions, and I'm guessing that many of the other ones that you'll pick up on cheap sites off the internet might not either. But fortunately, there does seem to be a fairly standard convention for the color coding of the wires coming off. So assuming yours is the same as mine, the convention is that the red wire coming off the load cell needs to go to the E+ connector on your HX711. That's the positive excitation. The black wire goes to the E- side. So that's a little bit like your sort of ground and power supply, like normal. The white wire goes to A+, and the green wire goes to A-. Now, on the version of the HX711 module that I'm using, it was a 2-channel module, so I also had a B+ and a B- pin over here. But because we're only using a single channel, you can just leave those blank and ignore those. Okay, so that's wiring the load cell into the HX711. And then on the other side of the 711 module, there's 4 connectors here. So you need a ground line going to the Arduino, and also a 5-volt supply here as well. And then the 2 wires in the middle there, one of those is a clock pin and the other is a data pin. So the white wire here is going into the data line of the HX711, and that is going to the A0 pin on the Arduino. And then the orange line I've got here is going from A1 to the clock pin here. So my labels here on my particular module were called, I think, CK for clock and DT for data. Yours might be labelled as SCK sometimes for system clock, or it might say clock, or DT or data, but those are the 2 lines there, and you'll go to A0 and A1. You can use any other pins on the Arduino you want. Those are just the 2 that I use in the code, so if you want to use my code exactly as it is, then those are the 2 pins you'll need to use there. And then on the other side of the Arduino, if you've followed any of my other puzzle videos in the past, this will probably look quite familiar to you. So I've got a 5-volt relay module here, and it's 5-volt because it has a 5-volt supply to trigger it on the input side. So here we've got that wired to ground and also to 5 volts coming from the Arduino, and then it has a single signal line as well, going to the third pin, and I've got that connected to the digital pin 2 on the Arduino. Again, you could use any of the other pins you want, it's just that that's the one that I'm using in my code. And when that signal line is written a high signal onto that, what that's going to do is that's going to flip the relay over to connect these pins on the other side. So on this side I've got a 12 volt DC supply, and the positive 12 volt supply is going to the normally open connector on the relay. I've got the common pin in the middle is going down the red line to the positive supply on the MagLock, and the negative lead from the MagLock is going back to the DC input again. So when the relay is not activated, because we're using the normally open connector here on the relay, these two wires are not connected. There's a break in the circuit here, so the MagLock is not powered and it remains locked. When the load cell detects the correct weight item on it, which is detected by the Arduino, what happens is this signal line here has a high signal sent down it. That closes the relay, switches it across, which connects these two, and that allows current to flow on this side of the circuit. So the 12 volt connector here powers this MagLock, which then releases the catch, and the puzzle is solved. Okay, and now let's have a look at the code. And there's a couple of new features that I've used in this code that I haven't shown in any of my other puzzles. So I'll step through it line by line and hopefully explain those as we go along. So to start with, as always, I define a flag for whether I'm debugging the code or not. So when you want to have additional information about what's going on in the code, you leave this line here, and as the code runs it will send additional information over a serial connection back to a PC. When you're in production and you don't need that information, you can simply comment the code out like that. Now, unusually though, this is the first puzzle I've used another define flag as well, and that is because when you first set this puzzle up, you need to calibrate the load sensor so that it has a correct 0 value and that it is weighing the correct range of weights. So I've actually got an additional sort of mode that can be set for the program here, which is whether you're in calibration mode or not. So you will always need to do that at least once when you first run the program and you set your puzzle up. You may need to run it again in the future if you ever change anything, or change the style of hook that you have on the end of the load or something like that. But once you're running and you're in production, you can sort of safely comment both of those lines out like that. I'll explain more what they do in a bit later on. So I'm using two additional external libraries to run this code. The first one is a library for interfacing with the HX711 module itself, and you can download that for free from the following GitHub link. And the second library I'm using is a library that comes with Arduino itself, but you do need to include it, and that is for something called EEPROM. Now, normally when you run an Arduino code or something like that, you upload the code to the device and you power it on and you run it, and every time you turn it off, there's no way of sort of saving the state of a puzzle between powers off. Every time you turn it on again, it starts from as if it was the first time it had ever been turned on. Now, as I explained sort of above, this puzzle is going to need a little bit of calibration data, and it would be quite annoying if you had to recalibrate the puzzle every time you turned it on. So what we're going to do is the first time you turn the puzzle on and you calibrate it, it's going to work out a few values which it's going to need to make accurate weight measurements, and then it's going to save them onto a small piece of memory on the Arduino, which is called the EEPROM, which is, I mean, you can think of it like a tiny little hard drive, I guess. It's very small, and you can only write a few items of data to it. but it's perfect for this scenario. So I'm including that library there as well, just so we can persist data on the Arduino between turning off and turning it on again. Okay. So then we move on to a section about constants. So these are values that are going to always be the same every time the puzzle is run. So the first thing I'm doing is I'm defining a thing called a signature value. So when we try to load that configuration data from the EEPROM, the very first byte of the data that we're going to save is going to have a known value. And I'm just using the value 100 here. There's no particular reason for that. It could be any value you want. But it's going to be a known value. And that's it's a little bit like a checksum, just to say if this is the first value that's in the memory on the Arduino, then I know that this is a valid piece of configuration data that's been written. So it's a fairly kind of simplistic check, but it's just a little bit of additional information to make sure we don't read some arbitrary data that's been saved into memory and try to load our configuration based on that. So I'm just using the value 100 there as a slightly arbitrary value. Here's our pin definition. So this is the pin that the relay is going to be attached to on the Arduino side, so we're using digital pin 2. Now this value here, this is going to be the solution weight. So this is going to be the target weight that we want the total, all the items that have been placed on the load cell to equal. If you saw if you rewind the video and go and play the first sequence again, you'll see when I place the bell on, the weight of that, well, I think 475. And I'm allowing a tolerance of 10 either side. So this is in grams, because when we've configured and calibrated the scale correctly, the readings we'll get will be in grams. So I'm accepting an answer weight of 476 plus or minus 10 grams either way is going to solve the puzzle. And then we move on to the global section. So this is going to be parts of the code that we're going to access across all of the different functions as we go along. And we're going to create a new HX711 object. So this is the main object that's added from the HX711 library. We'll call it scale. And we'll define the two pins that the scale is plugged into. So that's the data pin and that is the clock pin. The next line here, we're going to define a scale factor. This is going to be one of the values that is going to ensure that we actually get correct measurements. Now, this value here is going to be overwritten when you run the calibration routine anyway. So this was a value that I was using during testing, which was correct for my particular setup with the load cell and the position of the weights and where I was hanging the hook and things like that. Yours may be different, but you're going to overwrite that later on anyway, so don't worry too much about that value. And then lastly, we have the various states that the puzzle can be in. And this is quite useful to keep track of sort of what's going on in the puzzle at the moment if you ever need to debug anything. So it starts off in the initializing state. While the players are trying to solve the puzzle, it will be in the running state. And after they have placed the correct combination of items of the right weight, it will move to the solved state. Okay, so now we move on to the different functions. And this is the function that is going to load the data from the EEPROM memory on the Arduino. So remember I said that we were going to write that signature little value to the first byte. So this line here says if the very first address of the EEPROM memory, we're going to read that address, and if that's equal to the EEPROM signature, that means that we know that the data written there is valid. So we're then going to get the rest of the data from the EEPROM. So we're going to start at 1 this time because we're going to ignore the signature byte, read the rest of it, and we're going to load that into that scale factor value up here. Remember I said that was going to be overwritten. Well, this is the line here that's going to overwrite that with the value from saved onto the EEPROM instead. And if we're in debug mode, what we'll do is we'll just send a little bit of output to the serial connection just to say that the calibration data has been loaded, and it's going to output that onto the screen. If the signature isn't valid, then we fall into this part of the code instead. That's just going to say, okay, if the signature is not valid, we'll send a message to our debug output saying that we couldn't find calibration data. And this is the kind of the system method of the one above. So this is saving the calibration data to the EEPROM. So what we'll do first of all is we'll write a 0 byte into that signature address at 0. So if any of the following stages of this method fail for some reason, that first byte is going to be 0. It's going to be invalid. And that will mean that if we ever tried to load it again, this line here would fail. I hope that kind of makes sense. So the first thing we do when we're saving new data is actually to deliberately invalidate what's there at the moment. And then we're going to put the scale factor into EEPROM. And then if that's successful, we're then going to put the signature back at the beginning again to say, okay, it was successful. Now we'll say it's valid. Let's put that valid signature back at the beginning. And if there's any problems, again, we'll write a message. So I hope you can see actually using the EEPROM to save data is really simple. It's this, you can read data with this read. That's just going to read a single byte at the beginning. You can get a whole value and replace a variable's value with something from the EEPROM itself using get. And then when you want to save stuff onto the EEPROM, you can use this put method here to put a variable into a memory address, and you can use write to write an individual byte. So it's pretty straightforward to use actually, and it's very useful. So you might want to use that in other situations as well. This next method is the onSolve method. So this is what's going to get called when the puzzle is successfully solved. And again, this will probably look fairly familiar to you. Now remember, I'm using a fail-safe MagLock here. So I don't need to maintain a persistent current to the MagLock to keep it closed. It will stay closed by itself automatically. To release it, all I need to do is to send a brief current to it, and that will spit out the latch, and then I can turn the current off again. So when the puzzle is solved, what I'm going to do is I'm going to write a high signal to the lock pin. So I'm going to send 5 volts to the relay. That will activate the relay, close that connection, spit the latch out. I'm just going to wait a second just to make sure that it's definitely had enough time to do that process. And then I can reset the relay with a low signal again, just so I'm no longer powering the MagLock. So the whole of the unlocking process only requires 1 second's worth of current going to the MagLock, and then it just turns off again. And I'll advance the puzzle state to solved when that's done. Okay, so now we get the setup function. So all of the functions up to now have been kind of helper functions that are called by various other points in the code. Setup is actually where our code will begin running. So if we are debugging or if we're calibrating, then we're going to open the serial connection because that will be required in order to see some of the output values for calibration anyway. And this next section is about how we calibrate the scale. So there's a series of steps you've got to follow to do this, and it is actually described on that GitHub page where the library came from as well. But I'll sort of talk through it. So the first thing you do is going to call this set scale function, and that's kind of like a resets the scale to its default value to start with. And then you call the tear function after that. So tear is the kind of 0 weight when there's nothing on the scale. So these two things are kind of saying reset to default, basically. Initialize everything at one scale factor of 1 and 0'd when there's nothing on the scale. Okay. And then the next thing we're going to do, so we're actually going to put some instructions onto the serial connection so that whoever's running this can see what they've got to do. And it says place a known weight on the scale and type its mass in grams. So if you've got a kilogram weight, or if you've got a 500 gram bag of sugar or something like that, anything that you definitely know the weight of, you can place it on the load cell at this point. And this line here, while not serial available, what that line there is going to do is that is going to keep repeating that line until some sort of input is sent over the serial connection. So what that basically means is it's going to wait indefinitely on this line of code until the user types this mass in grams that's been requested up here. When they do, it's going to fall through to the next line. So serial pass int means whatever value was typed in here, we're going to pass that as an integer value, and we're going to assign that to a variable called known weight. What we're then going to do is take a reading from the scale. So with this known weight on it, we're going to say, okay, what value are we getting back from the scale with this known weight? And this 10 at the end means to take an average of 10 readings, just so we can eliminate any noise that we might be getting here. Okay, so we've got a known weight, and we've got the reading that that known weight gives us. We can then calculate the correct scale factor by dividing the reading by the known weight, and then what we'll do is we'll print that to the debug connection, to the serial connection, and then we're going to call that save calibration method that we saw earlier up here. So we're going to, having calculated the correct scale factor, we're going to write that onto the EEPROM, which means we don't have to do this every time because we just load it for next time. And then we'll just dump a bit more information here. So we'll now say, okay, the calibration's done. You can now take the weight off and send another key to carry on the code. And then, so again, we wait here until they've done that. And then we'll carry on. Now this load calibration here, so this else statement comes with the if def calibrate. So if calibrate has not been defined in the code at the top, then we'll load the existing calibration again. So if calibrate is set, we'll call all this stuff here. If it's not, we'll just load whatever the last calibration that's saved was instead. And then we set the scale factor on the scale that's been calculated. We reset the scale again back to 0. We make sure that the lock is not locked because we're using an active low lock here. Sorry, that should say relay, not LED. I think in the initial version of this puzzle I was just lighting an LED, but I've obviously changed that to a relay now. And we've finished our setup, so we'll set the puzzle state to running. And now we're in the last, the main method of the code, which is also the last one in the code listing. So what happens here depends on what state the puzzle is currently in. We shouldn't ever get here and have the puzzle state initializing because setup is always called before loop, and the very last stage of setup was to set the puzzle running. So the puzzle can be running, and if it's running, what we're going to do is we'll read the scale 5 times, and we'll take an average of those 5 measurements and we'll assign it to something called value. If we're debugging, we'll just display what that reading was. And then we'll say, okay, if the value less the correct value that we're looking for, so the solution weight that we assigned at the top, that was that 475 grams. If the absolute value of that, so if it's either plus or minus, is within the specified tolerance, we'll call the onSolve method. So if whatever's been placed on the scale, if the reading that has given us is within the accepted tolerance of the solution weight, call onSolve. If it's not, what we'll do is we'll simply wait for half a second, and then we'll repeat again and we'll take a new reading. That's just to sort of slow the code down a bit. There's no need to poll the load sensor sort of 50 times a second. And actually that delay helps a little bit. When people are taking things on and off the scales, you kind of want to wait a little bit for it to be stabilized before you take the reading. So that just slows down the rate of reading the scale. If the puzzle has been solved, we don't need to do anything anymore. We'll just break. So break will just say, okay, quit the loop, come around again, and every time it will continue to quit. So this is what we describe as a latched puzzle solution, in that once it has been solved once, it will remain solved forever. So there's just a few more things I'd like to demonstrate, particularly around the calibration of these scales, but also a little bit about, you may have questions about how accurate and how fine a level of granularity that load cell can detect. So I just want to try and demonstrate that as well. So first of all, the calibration of the scales. So for a bit of a change, I've hung this very hastily manufactured container, which I'm hanging from the bottom of the hook here. This is an old ice cream tub. I should just mention the load cell will work just as well whether you are pulling a weight down on it from a hook like this, or whether you have a sort of a container on top of it that is pushing down. It totally depends on how you want to configure your puzzle. I personally prefer a hook hanging down. I think it's a nicer aesthetic. I think it's more interesting to hang things on a hook than to place them in a container, but you can do either. And here I've got a kind of a combination of both, because I've got a container that I'm now hanging from the hook. So what I'm going to do first of all is I'm going to show you that calibration routine and what that looks like. So if I reboot the Arduino, the first thing you'll see displayed is that message that was sent when calibration mode was activated that tells you to place a known weight on the scales. And here I have a bag of flour. This is a 500-gram bag of flour, which I'm now going to place into my scale container there and weigh that down. And what the prompt tells me to do is to type the mass in grams of the weight on the scale. So I'm going to type 500, hit enter. So that is now going to take 10 readings with that known weight on the scale and average them out. And it's calculated a scale factor based on that, and it's saved it to the EEPROM, and it now says to remove the weight. So I'm going to remove the weight again, and I'm now going to send another keystroke. So I just send a Y. You can't just hit enter. You do actually have to send some value back to the serial connection, just so that it knows that the weight has been removed. And so that has now set the scale for the load. And you can see that the reading coming up is 0. So now that the scale is configured, let's see how good it is at reading more sensitive measurements of small items. So I've got here a number of pound coins. These are UK £1 coins. And according to this website I found, which is the Royal Mint of the UK, this coin should weigh 9.5 grams. So if I pop one of these into there, let's see what reading we get. We get a reading of, well, we had 9 and then we've moved up to 10. So that's not bad, I'll take that. If I add 2 in, so we would expect that to be 19. Sure enough, we're getting a reading of 19. This is going surprisingly well. If I add 3, we're going up 29. Yeah, that's okay. 4 and 5. So 5 lots of 9.5 is, yeah, it's pretty close to 47. So yeah, I'm actually quite pleased with that, to be honest. This is obviously quite a makeshift setup I've got here at the moment, because I'm holding it by hand and it's wobbling a bit, things like that. So you would normally want to set yourself a bit of tolerance either way. It is worth pointing out as well that the load cells themselves can come with different kind of ratings of the maximum weight that they can take. So this is a 5 kilogram load cell, and obviously you'll want to get one that is at least rated high enough for the total weight of items that you're going to place on it, but not so great. The higher the load it can take, the less sensitive it will be. So what you want to do is get one that's at least as big as the total weight, but the smallest one that is greater than that. In terms of their robustness, obviously you don't want to hang something that's completely way too heavy on the end here. You will snap the cell if you place something too great. You could put a physical sort of a stopping restraint on this end here that would stop the bar if it tried to bend too much. The other thing you could do is in software, obviously we've already got that code in there that's checking what the weight is that's being detected in the Arduino in order to activate the relay. What you could also do is add another test in the code that says if the weight detected on the load cell was too great, to activate some kind of warning LED or shut-off or sensor to the player that made it clear that they were placing too great a load on the load cell here. But actually, as you can see, the sensitivity itself with quite small items is actually pretty good. So I'm quite pleased with that. So that's about all there is to say about this puzzle, really. I've not dressed it up very well here. As always, what I want to focus on really is showing you the electronic components involved. But there's lots of ways you can easily imagine a number of items or choosing from one of a number of items of the correct weight. And it's a nice alternative maybe to RFID, which is commonly used for identification puzzles, to use weight as a possible way of identifying what a correct item was instead. But if you've got any questions, as always, please let me know in the comments. I'll put the wiring diagram and the code and where I got all these components from. I'll put links to them in the description as well. And thanks very much for watching.